This is Chintan Patel and welcome back to the video lecture series of the fundamentals of machine design. In this lecture, we are going to cover the topics under your syllabus that are the power screw and the threaded joint concepts. In this lecture, we will see those concepts in order to get the concepts regarding the procedure to solve the examples related to them. And that's why it is very important to refer this lecture before starting the or understanding the method or procedure to solve your examples based on this. So it is going to be the very important lecture for this examples, as well as in your examination they can ask you this type of a theories for the 7 marks or the 5 marks, and based on the theory marks you will have to explain each and every terms with briefly. Now we will see the definitions based on the different theories and terms related to them which you need to understand before starting the theoretical portion. The first term is the power screw. The power screw is a screw and a nut system used to convert the rotary motion into the linear motion and to transmit the power. So whenever it is required to transmit the power from one end to another end, or it is required to rotate the to convert the rotary motion into the linear motion, that type of application will give you the be satisfied using the power screw. The power screw examples are shown in this figure. As you can see, the power screw can be utilized in various applications as well. As you can see, the first diagram indicates the power screw for the lifting jack, as well as the second diagram indicates the power screw for used in a lathe machine. The applications for this type of a screw is to raise the load in a screw jack, to obtain the accurate motion in the machining operation, just like a lathe screw of the lathe machine, to clamp the workpiece in a vise, and to load a specimen in a UTM. So these are the various applications in which the power screws are most probably utilized. Now we will see the terminology regarding the power screw, and for terminology we have a basic diagram indicating those terminologies over here, in which you will find 3 different diameters, D, DM and DC, and there is one angle which is also known as an helix angle, pitch and lead. All this terminology is represented over here. The nominal diameter, which is represented by D, it is the largest diameter of the screw. It is also called as a major diameter. The core diameter DC, it is the smallest diameter of the screw thread. It is called the minor diameter. And the mean diameter DM, it is the average of nominal and the core diameter. So the pitch is the distance measured parallel to the axis of the screw. The axis of the screw is vertical over here, and it is the distance measured parallel to the axis of the screw from the point on one thread on the thread to the corresponding point on the another thread, or which is adjacent to the first one, and that's why the pitch is the distance measured along the axis. Now we will see another terminologies regarding that figure, that was the lead L. L is the distance measured parallel to the axis of the screw. It is distance measured parallel to the axis which the nut will advance in a one revolution. If you rotate the nut for the one complete revolution of the 360 degree, then how much distance it covers or it advances is represented by the L, and which is known as the lead. So lead can be calculated using the mathematical form L equals to N into P, and N is the number of start of the thread. So the helix angle is the only terminology which is left, that is represented by the lambda. It is an angle made by the helix of the thread with the plane perpendicular to the axis of the screw. Now this helix angle is already represented on this diagram, but we need to explain it a little bit more in terms of the mathematical form. That's why we have represented one triangle which is created just by unwinding the thread from the circular form to the straight line. If you unwind the threads, then you will get this line, and by considering the angle between those lines with the reference horizontal line, then perpendicular axis, then you will get this angle or a lead angle or the helix angle. By the calculation of the trigonometry, you can directly calculate the value of 10 lambda tan lambda is equals to opposite side upon adjacent side, and opposite side length is lead L, and adjacent side lead length is the pi dm, that is the perimeter of the thread or the screw, and by which you will be able to calculate the angle, helix angle or the lead angle. Okay, so this was all about the terminology that you need to understand before starting the theories. Now we will understand the power screw thread forms. What are the different types of the forms which can be utilized for in the case of the power screw? So the first one is the square thread, and the diagram of the square thread is represented on your screen, where you will find a cross section of the thread as a square. As you can see in the diagram, the square thread is having the height or the depth of the p by 2 and the width of the p by 2, because it is square, and that's why each and every sides of the square must be equal. Now there are few advantages. It has the maximum efficiency of all the thread form and transmit the power in either direction. You can go upward or downward. It is possible in the case of the square thread. The disadvantages of the square threads are the strength is the lowest in of all the threads. Whether there are number of the types of the threads available, but this type of a thread is having the low strength, and it is very difficult to cut. So the manufacturing of this type of a thread is also difficult. So the application of this type of a threads is limited to the screw jacks and the mechanical presses. So wherever the high efficiency is required and low strength is permissible, then you will be able to utilize this type of a thread. Now another type is the trapezoidal and the acme thread. As you can see, the diagram of those thread is represented over here, and the advantages of this type of a thread is stronger than the square thread. So whenever the strength is the criteria for the design, then you will be able to select this type of threads over the square thread. That it can transit the power in the either direction, and that's why it can be easy replacement of the square thread. But it has one disadvantage, is that it has a low efficiency than the square thread. So if you want to compromise with the efficiency factor, then you can go with the trapezoidal of the acme thread. But if the efficiency is your criteria, then you must go with the square thread only. So the application of this type of a thread is the bench wise, where the strength is required and efficiency is not a big thing for the design point of view. So we will see another type of the thread that is already represented in the screen like here, that is the buttress thread. It is used to transmit the power in any one direction. So that is the only one design criteria while selecting this type of a thread. So as you can see, the diagram of the buttress thread is represented on your screen. The advantages of this type of a thread is it is stronger in a shear than any other form. So if you want to have a better strength in shear, then you can go with the buttress thread. High efficiency of the square thread and high strength of the V thread, both are combined together in this type of a thread. The disadvantages of this type of a thread is to transmit the power in only one direction. So if your application demands for the power transmission in any direction, in either direction, then you cannot go with this type of a thread. And the applications of this type of a thread is used in a vise and the screw jacks. So this was the very important modification. Now we will see another theoretical part about the torque required to raise the load. Now the torque required to raise the load is represented in the diagram like this, where you will be able to connect this type of a diagram with the phenomena of the lifting the car with the use of the screw jack, where the load is vertically downward, the weight of the car, and you need to lift the car with the help of the rotation of the screw. Now if you are considering the lifting of the car, then the car load will be uplifted, or it will be slided up on the slant thread sides. Okay, and that's why the diagram of the load motion would be on the slant edge, which is represented by the block diagram in the right side of the screw thread. Now, if you want to derive the equation for the torque required to raise the load, then you must understand the different terminologies that we have already used in this diagram. That is, the W equals to load, P equals to effort, the Fr equals to friction force, that is the mu into N, that is the basic definition of the friction force. N is the normal reaction considering the system in equilibrium under the action of all the forces. For horizontal equilibrium, sigma h equals to 0. So if you consider the horizontal or each and every forces and take the algebraic sum of all the forces based on the direction, then you will be able to conclude your equation with the equation number 1, that is the P equals to mu into N cos lambda plus N sin lambda. Now we continue our derivation in the upcoming slide, that is this one. For the vertical equilibrium, N cos lambda minus mu N cos sin lambda minus W equals to 0, that is the algebraic sum. Now if you consider the simplification, then you will get the equation number 2, that is W equals to N cos lambda minus mu N sin lambda. Now divide the equation number 1 by the equation number 2. If you divide those equations, you will get this, the ratio in the manner of the P by W equals to something like represented on the screen. Now if you simplify that by dividing the right side by the cos lambda, if you divide the whole right side by the cos lambda, you will be able to find the ratio of the sin lambda and the cos lambda, which is also known as a tan lambda. So if you put the value of the tan lambda and mu equals to tan phi, that is the basic relation in the case of the friction, then you will be able to simplify the equation in terms of the tan phi plus lambda. So P equals to W into tan phi plus lambda, and the torque required to raise the load is T, which is equals to force into radius, and the force is the P, and we have the value of P and we have the value of the radius, that is dm by 2. So torque required to lift the load is given by this formula, that is the W into dm by 2 into tan into phi plus lambda. So that was the derivation of the torque which is required to lift the load. Similarly, you will be asked in your examination to find the value, to find the torque required to lower the load. The only thing that is changing in this derivation is the direction of the motion. We continued our previous derivation with the assumption that we are going to lift the load in an upward direction. Right now we are going in a downward direction, so the friction force will be in the opposite direction. That is the only change in this particular derivation. If you consider the direction change, then the rest of the procedure is the same, and similarly we can directly conclude to our final equation of this derivation, that is that T lower equals to W into dm by 2 tan phi minus lambda. That is our final equation, and you need to derive as well as remember this equation in case of while you are preparing for your exam, because you will be able to utilize this equation only if you remember it. So we go with the self-locking and the overhauling of the screw, and that is the major condition of in the case of the power screw. That is, the torque required to lower the load is T equals to W dm by 2, that is tan phi minus lambda. So if the screw is in a self-locking condition, then phi, that is the friction angle, must be greater than the lead angle. So if torque required to lower the load will be positive. So the application of the screw jack and the C clamp works based on this condition. Whenever you rotate the screw in a vertical direction to lift the load, then it will lock itself at the position wherever you leave it. So that condition is known as a self-locking condition. Now the overhauling condition is the phi is less than or equals to lambda. Whenever this condition is applied, the torque required to lower the load will be negative, and negative torque indicates that you do not need to apply any torque. The screw itself will rotate and your the load will be lowered down automatically. You don't have to apply any forces, and this type of application is also very popular in your industrial zone, where where the effort is reduced for the workers, and the screw efficiency and the screw efficiency of the power screw is represented by this equation, where we have taken the torque required without the friction, ideal torque input, and that is the torque pi dm by 2 into 10 lambda, where we have considered the ideal torque input where the friction is neglected, and that's why we have not written the value of the phi in this equation. Now actual torque required is this represented by this equation. Now if you compare both the torque and take the ratio of them, then you will be able to calculate the efficiency of the screw, that is 10 lambda upon 10 phi plus lambda. Now work input, alternative method to calculate the efficiency of the screw is work input. So if you want to calculate the work input, then torque into displacement of the torque will be your work input, and work output will be load into load displacement of the torque, that is the load, that is W, and displacement of the load is L. So if you take the ratio of both of them and simplify, then you will get the answer of the efficiency in terms of the WL upon T into 2 pi. So this is the basic criteria where we have considered both the equations of the efficiency of the screw. Now we will see another theoretical portion of this lecture, that is the collar friction of torque. Now if you consider the collar, or the collar which is required to impart the rotary motion without the rotation of the screw, then you will have to consider the collar friction, and collar friction can be calculated using the two different theories, uniform pressure theory and uniform wear theory. Both the equations should be remembered by each and every student in order to calculate the collar friction in your examples. So with this you will be able to understand the theoretical portion of the power screw and threaded joints, and in the upcoming lecture we will start our lecture with the examples and the list of formula based on which the examples can be calculated. So with this we conclude our lecture over here. Thank you.